Hi, in this lecture I will be focusing on the A to D and D to A conversion process, the sampling process, sampling and holding process, discussion on the Nyquist sampling theorem, discussions on the D to A and A to D converters. Okay, so let's start. Firstly, I will be opening up my discussion with A to D conversion, and afterwards I will be following this sampling process discussion. What is A to D conversion? It is a process in which an analog signal is converted into a digital signal, and for that we do what is that we have two processes. One is the sampling process. In this process we will be doing discussion in this topic, and we have another process which is the sampling and holding process, which we will be discussing over here. So sampling, what is sampling? Sampling is the discretization of the time domain of an analog signal, and for sampling we use a kind of impulse train signal, and that impulse train signal is applied at the gate of a control device, and the drain to source is drain is having a kind of analog signal, and the source is having a kind of digital signal, and the sampling signal is applied across the gate, which activates that devices and moves across the input signal to the output signal, and in that way we retrieve a sampled signal of the analog input. So sampling is a kind of process in which we make use of any impulse train, and we get output in the form of a sampled version of the analog signal when we are having and at the site of the input the analog signal. So the signal which is coming on the side of the output, this kind of signal is being said as a pulse amplitude modulated signal, and the sampling process is I have explained earlier as well. This is a kind of process in which we have a transmitter, which is a control device, in which we have a gate where we apply the sampling pulses, and we have the source where the output is coming in the form of a sampled signal, and we have a drain where we apply the analog signal. And if we discuss about the waveforms, then this is demonstrating the analog signal of voltages till 5 volts, and this is indicating the sampled signal which is applied on the side of the gate, and this is demonstrating the output sampled signal. So the duration of this pulse is an issue in the sampling circuit, because the A to D converter needs some more time to do the decoding or encoding of the analog signal. So in order to represent that pulse in the form of binary bits, the A to D converter needs some time, and this is a kind of short duration, because in that short duration the A to D converter is not very efficiently or in a fast manner. If the signal is coming at a fast rate, the A to D converter is impossible for that to do its conversion with this short duration wave. So this is a kind of issue in the sampling circuit. So what we will be using for that, we will be using a sampling and hold circuit, which is a kind of providing a modification in the sampling circuit by adding a capacitor element, which is a holding device over here, which is increasing the time duration of that short duration time to a large duration time like this one, and in that way the issue of the A to D converter is resolved, and which can decode or encode the samples into binary codes at a very fast rate, and it will not be an issue. So this is a kind of sampling and hold circuit in which the same arrangements, just by adding a capacitor holding device element, and the sampling circuit was only providing us the sampled signal, while this signal is providing us the quantized signal, which is a next level of the sampled signal. If we discuss about the waveforms on the drain, gate and source, then this is the output signal of the sample and hold circuit, while these are the sample this is a kind of sampled version which was retrieved, and by the capacitor device this sampled signal was enhanced into the quantized signal by the sampling and hold circuit, and in that way the issue of the A to D converter is resolved with the help of a sample and hold circuit. Now we will be doing discussion on the Nyquist sampling theorem, which says that if we want to convert any analog signal into digital signal and then to recover analog signal from that converted digital signal correctly, we need to sample the analog signal maximum frequency multiplied by 2 frequency of the samples. So mathematically it is how telling us about the sampling theorem. This mathematical model is telling us that the sampling frequency, the rate at which the samples are coming in, has to be equal to or greater than twice the maximum frequency of analog signal. Like we have any voice signal which is of 4 kilohertz and its frequency is varied from 2 kilohertz to 4 kilohertz, and the maximum frequency of the voice signal is 4 kilohertz, and multiplied by 2 means that 8 kilohertz. So the sample's frequency has to be 8 kilohertz or greater than that if we need to recover our analog signal correctly from that sampled version of the digital signal. This is what is being said by this uh, Nyquist sampling theorem. So we have to prove it, the Nyquist sampling theorem. There are two ways to prove it, either in the time domain with the help of convolution as indicated by this mathematical model, and the second one is the frequency, in which it can be proved in the multiplication operator in an easier manner. So we can see that in the first way we have, this is the output which is coming on the side of the source, and this is this is the input which is applied on the side of the drain, and this is the sampled signal which is applied on the side of the gate of the transistor, and this is a com com complex kind of operator in the time domain. We have a way to solve it in this manner as well, while we have another way. We can do its transformation into frequency domain, and we're doing its Fourier transformation, and we know we have a proof that convolution in the time domain is equal to multiplication in the frequency domain. So this is a frequency transformation of this equation, and in this we already know that the ST, which is indicating a train of impulses, can be represented by this delta T, and these are the number of samples coming after some regular time period interval, which is the sampling interval, which is represented by capital T, and reciprocating it with the frequency, we know that this is the sampling frequency. So doing its Fourier transformation, we are resulted with this, and then placing its value over here, we are getting this, and we have the output, we have the input, and we have the transformation of the impulse train, and opening that expression we get this expression. This is the mathematical model, and this is representing a kind of uh, representations in the frequency domain like this, where each semi-elliptical circle, its magnitude is represented by this ws into xw, which is coming over here in every expression, ws into xw, and the shape of that semicircle is of the shape of the input signal, and it is dependent upon this input signal, and then this uh, uh, omegas are indicating that impulses are coming at various different times, and the bandwidth of those semicircles are equal to 2 Wm, where Wm is the maximum frequency of the analog signal. So we have three cases of this mathematical model. One case is that if we have the sampling frequency which is greater than twice the maximum frequency of the analog signal, then we have each semicircle, elliptical circle, which is representing the information at a at a distance of separated from each other quite clearly over here, and each semicircle is no semicircle is interfering with the other semicircle, and the information is safe. While if we have a scenario in which we have the sampling frequency is equal to twice the maximum frequency, then we have this kind of uh, demonstration in which the information is also safe and no semicircle is interfering with any other semicircle. While if in the third scenario in if which we have uh, the sampling frequency smaller than twice the maximum frequency of the analog signal, then each semicircle is interfering with the other semicircle, and it is causing an intersymbol interference, which is causing the effect of aliasing, and it is a kind of loss of information, and we have to use some anti-aliasing filter to recover the original lost information. So this is not a good scenario over here. So we have to follow the Nyquist sampling theorem, and keeping our sampling frequency twice multiplied by the maximum frequency or greater than that, in order to keep our information safe and save us from uh, the anti-aliasing filter. So that's how we have proved the Nyquist sampling theorem, that we have to obey this mathematical formula, otherwise the aliasing happens, and when the aliasing happens we have to use the anti-aliasing filter. Now we move to the next topic, and before that I will be doing some discussion on the interpolation, which is a kind of terminology which is giving us a way by which if we convert any analog signal into the sampled signal, which is a digital signal, then how to recover from the sampled digital signal the original analog signal. So we can use the interpolation. Interpolation is a kind of mathematical model. It is a kind of way by which we adopt in order to convert our sampled digital signal into an analog signal. Now we will be looking at the two topics, which are the digital to analog converters. We will be discussing that as well, and then I will be discussing the analog to digital converters, this one. So we can start with the digital to analog converter. What is a digital to analog converter? It is a kind of box which is indicating the D to A converter, which is converting a 4-bit or 8-bit or any bit binary number into a decimal value. The decimal value is indicating the analog signal, and the binary value is indicating the sampled version of the analog signal, which is the digital signal. So any device which is converting any binary input into a decimal input can be termed as a digital to analog converter, and we can see one example of it in the form of a binary weighted digital to analog converter, in which we have an active device which is the op amp, negative feedback op amp, in which we have done the ground of the positive terminal, and at the negative terminal we have some kind of feedback resistor, and we have some kind of resistors which are attached in this sequence, and this binary weighted DAC is converting 4-bit binary number into a decimal value on the side of the output. So it is converting any digital signal into analog signal. If we apply at this node the KCL, then which is saying that the sum of all the currents entering the node and leaving the node is equal to 0. So we can provide do the Ohm law formula applying over here and here, and we can say that I1 plus I2 plus I3 plus I4, these equal to IF, and we can do their voltage resistor ohmic relation we putting over here. We can rearranging them, we can do the calculation, we can do the simplification, we can do the cancellation, and then we put the values of the V1 to V4, and we can calculate easily the decimal voltage with the help of this binary weighted DAC converter. And this is a very simple example of the DAC converter. We have some complicated DAC converters and some many thousands and hundreds of DAC converters and very complex DAC converters which can be constructed in the integrated electronic chips of the DSP gadgets and which are beyond the scope of this subject. Now we will be doing some discussion on the analog to digital converter which are embedded in any kind of digital device is having these ADC which are embedded in that device. The DAC are embedded in that device. So any kind of device which is converting any decimal voltage into binary voltage is a kind of device which can be termed as a analog to digital converter, and we have some parameters before the example discussion of some A to D converter. We can see what is conversion time. Conversion time is the time taken by the ADC to convert any decimal voltage sample into its binary equivalent. This is a demonstration of the conversion time. So we have 2 volt sample. The time taken by the ADC to convert it into the binary equivalent is the conversion time of the ADC. Then we see the resolution is the kind of smallest voltage. The smallest voltage which an ADC can measure is a kind of telling us about the resolution, and resolution can be analyzed by voltage resolution as well over here with this formula which is involving the n bits of the quantizer and the full scale voltage which is the maximum voltage which an ADC can measure, and also it can be analyzed in the form of percentage resolution in this by this formula. And we have some problems in which we have demonstrated over here that we have an 8-bit quantizer and full scale voltage of 15 volts, and then what small kind of voltage the ADC can measure. So it can measure as small voltage as 5.88 millivolts, and we have done that analysis in the form of percentage resolution as well. Now we have different ADCs available nowadays, but the most common and most frequently used ADC is the flash converter, which is very much fast and which is using the comparator circuit in this way. And we have an encoder which is based on the combinational logic, which is very fast, and it is converting any decimal voltage into binary voltage. And comparator is a kind of device which is comparing two values, and if those values are equal, returning 1, and if the input value is small, then returning 0. Then if we have a 3-volt signal which is coming over here, then 3 is greater than 1, then it will be returning 1 over here. 3 is greater than 2, it will be returning 1. 3 is equal to 3, it will be returning 1. And if 3 is smaller than 4, it will be returning 0, but that is not the case in our scenario. So we have 3 ones which are coming over here, and those 3 ones are represented in the binary manner by 0 1 1 kind of binary output. And in that way this is doing the operation of the flash converter, and it is very much fast. And higher the number of bits, higher the number of comparator circuits we will be using over here, and it can be embedded in the DSP gadget with the help of the integrated electronics. And we have some advantages of the flash converter demonstrated over here, that it is having a fast conversion process and there is not much delay. It is very much highly accurate, and the resolutions depend upon the number of comparators to be used. It is very much complicated, but this complication is reduced by the use of the integrated circuit, which are VLSI, very large scale integration, or ultra large scale integration circuits, which can design by which we can design any kind of complex circuit in a very easier manner. And the cost of the ADC is for this flash converter is dependent upon the number of comparators, and it is very much used in our applications. Thank you very much.